Next, let's move on to topological sort. I really like this algorithm because it's one of those algorithms you can kind of learn without actually knowing it's an official algorithm. Suppose we have a graph that looks kind of like this. By definition, the topological sorting, aka the topological order of this graph, would basically be a sequence of each node itself. So in this case, we'll use the label of each node. So one valid topological ordering would be this: A, B, C, D, E, F. So when we call it topological sort, maybe sort is a little bit misleading, but that's just the name of it. In a sense, it is sorting, but it's not sorting an array. It's pretty open-ended because this is one valid topological ordering of this graph, but there's actually many. Let's talk about the definition of a topological ordering. Basically, given a graph like this one, a valid topological ordering is to say that for every single edge we have, such as this one, every edge has to be directed. So they have to have a direction. That's important because for every edge, a valid topological ordering guarantees that the source node comes before the destination node in the topological ordering result. So in the result here, you can see that yes, A comes before C, and we had to do that because of this edge. We also see that E comes before F. We also see that C comes before E. Not directly before, but in the general ordering, it appears first in the sequence and then eventually E appears as well. So basically with just these two edges, we're told that A has to come before C and C has to come before E. So implicitly, we know that A has to come before E. So you can see that that is the case. A is before E. That's just pretty logical in my opinion. So given this graph, it's guaranteed that A is going to come first in the sequence. Nothing else could come first because every single other node has an edge coming into it. So F has a couple edges coming into it, D and E, but it has nothing coming after it. So F is actually guaranteed to be the last in this topological ordering. A, of course, doesn't have anything coming into it. That's why it appears first. These siblings, sort of, though, are actually ambiguous because we know that for B, A has to come before it. For C, A has to come before it. That's all that's required of these two nodes, actually. So we wrote it like BC, but actually writing it like CB is also valid because there's no requirement on which one of these two has to come first. As long as A appears before both of them, then we're good. That's the idea behind topological sort. Another thing about it, though, it only works for graphs that are directed. We already talked about that. But also the graphs have to be acyclical. So we can only run this algorithm on a directed acyclical graph, aka a DAG. What if we tried running this on a graph that did have a cycle? Suppose from E we have another edge going back to A. What would happen in that case? Well, this kind of breaks the definition of topological sort because we know that A has to go before C. So we know we'll have a sequence something like this. A goes before C. C has to go before E. So we can have a sequence, something like that. And then we're told that E has to go before A. How is that possible? Because we know our sequence has to look something like this. So how can we possibly put E over here, but also have it come after the C? It's impossible. That's why topological sort does not work for cyclical graphs. But notice how I didn't mention the fact that the graph has to be connected. That's how this is different from a tree. If we had a graph like this where we have two connected components, this is actually valid. We can run topological sort on this. What does it mean though? Which one of these two has to come first in the ordering? Because this time, both of these do not have an incoming edge. So which one is going to go first in the topological ordering? Actually, it doesn't matter. That's why topological sort is pretty open-ended. There's a lot of possible solutions. With this graph alone, there's actually several valid topological orderings. One, the simple one would be what we had before, A, B, C, D, E, and then put G, H after that. But we could also rearrange this a lot. Like this GH is pretty independent of any of these. We could insert this right in the middle of this somewhere. We could put it before, we could put it after. It really doesn't matter. All we have to guarantee is that the G shows up before the H. That's all we have to do. The rest doesn't matter. And of course we have to preserve, the ordering of these as well. So given a directed acyclical graph like this one, that's not necessarily connected into a single component, it could have multiple components, how do we find a valid topological ordering? Just a single one, how do we do it? Well, we could actually do it with DFS or BFS. These are the two common traversal algorithms for a graph. So we could do it either way. We're going to be focusing on DFS. So how could we solve this problem with DFS? Well, let's just start at the beginning of each of these components, right? For example, this one, let's start at the beginning of it. Let's just start, printing each character or adding it to some result. Let's say we want to take each value of each node and then add it to an array, which represents the topological ordering. So this would be pretty easy, right? Start at A, do DFS, add A, then start going, down one of the branches. So this is our first neighbor of A. So let's start going down this branch. Recursively, now let's run DFS on B. So let's add B to the result. Let's go down B's neighbor. It just has a single one, D, add D to the result. D just has a single neighbor, add F to the result. And F does not have any neighbors, so we can't do anything anymore. So at this point, we would just pop all the way back up recursively, and then we would end up getting up to A. So then for A, we'd go to its next neighbor, C. So we'd add C to the result. Then we'd get to E, because C only has a single neighbor. Let's add E to the result. And this time, finally, we would get to F again. But in this case, we end up adding F to the result twice. That's probably not what we want to do. We don't want duplicates in our topological ordering. So how would we solve this problem? Well, to ensure we don't add the same node multiple times, because, one node could have multiple incoming edges. This doesn't necessarily imply that there's a cycle. So if this is the case, we don't want to add the same node twice. So the easiest way to solve this problem is by having a hash set. We'll use it to keep track of nodes that we've already visited before. This is not something new. This is something we usually do with DFS on graphs. So far, this algorithm is turning out to be pretty straightforward, but don't get your hopes up. Things can get more complicated. So when we get to F, we're going to find that we've already visited it before, so we're not going to add it to the result again. Also, we're not going to run DFS on this guy again because it could have had some, neighbors. It could have had another neighbor, maybe X or something like that. If that was the case, we would have already ran DFS on it once when we went down this path, and therefore X would have already been added to the result. So we wouldn't want to run DFS on F again because then we would end up adding, X again. So our visit hash set will prevent us from doing that. So now we've gone through one component. Next, we would just want to start at the beginning of the other component and run DFS on this guy. Pretty easy. Start at G, add G to the result, get to the neighbor, H, add H to the result, and we're done. We did that for the entire graph and we have a valid topological ordering. Well, we actually have a problem. Can you spot it? Take a look at our ordering. It's not quite valid, is it? And you probably noticed it a lot earlier when we got to this point where we got to F and then we added F to the result. The problem with doing that is, yes, before we add F, we have to make sure we add D to the result, but we also have to make sure we add E to the result as well. So how can we possibly know that we've already added all incoming edges of F? Like, we don't have necessarily an edge from F going to these guys, so we don't know that we've added them. So to solve this problem, there's actually two common techniques with topological sort that people use. I'll be focusing on the one that I think is easier, but I'll briefly talk about the other one. So let's talk about the one that I'm not going to go super into detail on. And that's because it requires sort of modifying the graph if the graph isn't in the form that we want. So let's take a look. Sometimes what people do is they'll take the graph and reverse it. That means they'll take every single edge in the graph and put it in reverse order. So if we had two edges going out of A, now we would have two edges coming into A from, its original neighbors. And that would be the case for every single edge that we have. And so now, instead of starting at, what we thought was the beginning of each of these connected components, we're going to start at the end of them. So this time we're going to start at F because it's the last node. But as we run DFS, before what we were doing, we were sort of running pre-order DFS where we added each element as soon as we visited it. But this time we're going to do the opposite. We're going to first get to 7. We're going to visit it, but we're not going to add it to the result just yet. Then we're going to go to one of its neighbors, D. We're not going to add it yet. Then we're going to go to its neighbor, B. We're not going to add it yet. Then we're going to get to its neighbor, A. We're still not going to add it. We're going to go to all the neighbors of A. It doesn't have any neighbors. Now we would add A to the result. And then when we get back to B, B doesn't have any more neighbors anymore. So then we'd add B to the result. Same thing with D. And then we'd get back to F. But before we add F to the result, we want to see, does F have any more neighbors? It does. So it has E, so then we visit E. But before we add E to the result, we're going to visit its neighbors. Do you kind of see why we're doing this? When we had the original edge going from C to E, what we were told, by definition, we have to have C appear before E in the result. Same thing for F. Before F goes in the result, both of the incoming edges have to be in the result before we can add F to the result. So we kind of reverse the logic here. We say that, okay, we'll go ahead and add F to the result after we add all of its descendants. And we'll add these guys to the result after we add all of their descendants. And we keep doing that. So we kind of reverse this, and I'll quickly run through this. So for E, we'd go to E's neighbors, C, and for C, we'd go to C's neighbor, A, but we already visited A, so we wouldn't want to add it multiple times. So then we would add C to the result, and then we'd pop back to E, we'd add E to the result, and then finally we can add F to the result. And we do the same thing with H and G. So we'd visit H. Before we add it, we're going to visit its neighbor, G. G doesn't have any neighbors. So then we can add G to the result, and then we can add H to the result. So you can see here, we do have a valid topological ordering. We make sure that A goes before any of these guys, and we made sure that F went after all of them. So this is the way that I don't prefer, because sometimes you can't modify the graph you're given, and I think modifying the graph is harder than what I'm about to show you right now. What I'm about to show you is actually easier. So this is the second way of doing it. What we do is we start at the beginning. We do the same thing where we don't add this to the result just yet. We want to add its descendants to the result first. But before we add those descendants, and we're going to do this DFS, so we'd go down one path first, so B, and then we'd go down D, and we'd keep doing that until we got to the base case like this one where this guy does not have any children. Then we would add it to the result. We'll add F to the result. And then when we pop back up to D, we'll add D to the result. And then when we pop back up to B, we'll add B to the result. By the way, we were able to add F because we know for sure it doesn't have any more descendants. Then we'll pop back up to A, but again, before we can add A to the result, we want to make sure we add its descendants. It does have another neighbor, C, so we'll get to C, but before we add C, let's add E. Before we add E, we got to add F, but we'll notice that F was already visited, so we're not going to do that. We pop back up to E, we add E to the result, then we pop back up to C, add C to the result, then we finally pop back up to A and add A to the result. We'll do the same thing for G and H. So we'll start at G. Before we add it, we got to add its neighbor, and H does not have any neighbors. So now we can add H, and then we can add G. But you notice something about this. Well, this isn't even close to topological ordering. Or is it? Because what we originally wanted to do is add A before we add any of its descendants. But what we ended up doing, since we did it post-order traversal, we did the opposite. We added all of its descendants, and then we added A. Same thing for G. We added G's neighbor before we added G. So actually, if we take the reverse of this, we will get the result. Reversing it will look like this. And this is a correct topological ordering, because just looking at one component, this left component over here, it's definitely valid for that post-order reasoning that I talked about. Now, we also had two individual components, these two guys, and we ended up, swapping the order of them. And, each one of these was individually reversed as well. Like this sequence shows up in reverse order in the output. This sequence shows up in reverse order here. And that's all we care about. Each sequence should be reversed. The relative order of each of these components, whether this one shows up first or this one, that doesn't matter at all when it comes to topological ordering. So this actually is a correct way to do it. So essentially what we found out is we want to run DFS on each of these components, but we want to do it in a post-order way so that when we build the output, our output is in reverse order. So what we can do after we're completely finished with building the output, we're going to reverse it, and then we will have a valid topological ordering. So that's all we really need to do. But there's one last catch that we actually have. We talked about the really simple case where we know exactly which nodes are, the head or the beginning of a connected component. But usually most problems aren't so convenient where we have that information. So if you don't know the beginning of each of the connected components of the graph that you're given, it's okay. You can still solve the problem in almost exactly the same way. As long as we have a list of every single node in the input graph, we can solve this problem. The only thing is, instead of us looping on each head of each component, we'll basically loop through every single node of every single component. Let me show you what I mean. Suppose, arbitrarily B shows up first in our list. So we would run DFS on B. We'd run it in the same post-order way. So first we would run DFS on its neighbor, D, then we'd run DFS on its neighbor, F, and then, F does not have any neighbors. So we would add F to the output, then pop back to D, add D to the output, pop back to B, add B to the output, and then we're done. Let's say next, C shows up in our list of nodes. Then we'd run DFS on C, and then we'd run DFS on its neighbor, and then we'd run DFS on its neighbor. We see though that we visited the same node twice, but that's okay because we keep track of the nodes that we visited in our visit hash set, so we don't end up adding F again. And as soon as we see it, we stop our DFS, we pop back up to E, we add E to the result, then we add C to the result, and then we're done running DFS on this guy. And so far, we've only run DFS on B and C. Let's say next we have to run DFS on D. Well, we would try to, but we'd see it's already been visited, so there's nothing for us to do. Maybe we run DFS on E now. Well, it's already been visited, nothing for us to do. Then maybe we run DFS on F, it's already been visited, nothing for us to do. So eventually we'd, try to run DFS on nodes we've already visited. It wouldn't work. So then eventually we would get to a node that we haven't visited. Maybe it would be A. But maybe to show you the more complicated case, maybe we end up running DFS on H. So then we'd try to run DFS on it. It has no neighbors. So then we'd add H to the output. Then maybe G shows up, so we try to run DFS on G, we go to its neighbor's already been visited, so then we pop back to G, add G to the output, and then there's only one node left that we didn't try running DFS on. Run DFS on this guy, try going to one neighbor, it's been visited, go to the other neighbor, it's been visited, so then we add A to the output. Now this is also a valid topological ordering. Well, of course, after we reverse it, we'll reverse it and then we'll get the real correct answer. But notice how this GH thing, is in the middle of the sequence that we created from this. That's perfectly fine because all we knew is that G has to show up before H, but this component is independent of the other component, so it really doesn't matter at all. So it turns out that this post-order DFS and then reversing the output works regardless of which order you run it. Whether you start at the beginning of each component or start right in the middle of a component, it doesn't matter. So now let's finally take a look at the code. So we're assuming that we're given a directed acyclical graph and we want to return the topological ordering. We'll talk a bit at the end what would happen if we weren't guaranteed that the graph was acyclical. But for now, let's assume that it is. Let's say we're given the number of nodes in our graph, and let's say, each node is labeled between 1 through n. And let's say we're given just the list of edges themselves. So one edge could be something like A to B. That would indicate that A shows up first and that B is the destination node. So it's a list of directed edges. And using that list of edges, let's just create our own adjacency list. This is a pretty common thing that you have to do in coding interviews. Usually you're not given an adjacency list. I think part of it is that it's your choice on how to best represent the graph that you're given. Usually adjacency list is the best way. This is just some boilerplate code that we've probably already seen before. But next is to actually run topological sort. So we have a reference. So we create an array. This is where our result is going to go, our topological ordering. We also have a visit hash set to make sure we don't visit the same node multiple times. And at this point, we do what I talked about, where we're just going to go through that list of nodes. In this case, we're going from 1 to n, just incrementing every single time. Maybe though, we could have been given a list of nodes as well, but usually this is the simple case. And for each node, so in this case, I is the label of our node. And what we're going to do is run DFS on it, just like how I talked about. So after we run DFS on every single node, we're going to have a topological ordering. It will be in our topological sort array. And then we're going to reverse it and then return it. So that's the main algorithm. Now, what exactly does our DFS look like? Well, it looks like this. Of course, we need to tell the DFS what node are we currently at, what's our current node or what's our source node at this point in time. We also have to pass in the adjacency list because for this node, we are going to want to go through all of its neighbors. So that's why we need that adjacency list. We also need the visit hash set because we want to know before we even run DFS on this node, has it already been visited before? If it has, we can return immediately. In this case, I'm returning, true, but it doesn't really matter. You wouldn't normally need to return true. You could just return anything. Notice how this function doesn't really need to return anything, and I'll get to that in just a moment. But if we know source is not visited, we want to make sure we add it to the visit hash set so that we never run DFS on it twice. Then we're simply going to go through its neighbors. So if we were at A, we would just go through both of its neighbors. We can get its neighbors from the adjacency list. That's kind of the purpose behind using an adjacency list. And for each of these neighbors, so B and C, we would run DFS on each of them, passing in the same three variables that we were passed in here. We would pass in the adjacency list, the visit hash set, and the topological sort array. We're not creating a new array every time we pass it in. So as we update the array, it will update the single global reference that we have. Well, it's not global, but it's a reference to that single array. And only after we run DFS on the neighbors of A can we then take A and add it to the topological sort. Because remember, this is sort of post-order DFS. And after we have done that, for every single node in the graph, we know our topological sort is created. And before we return it, we want to make sure to remember to reverse it. But now let's go back to that cyclical point. What if we were not guaranteed that the graph was acyclical? What would we do? Well, we would have to kind of augment this and add some cycle detection to it. One way to do that, the way I like to do it, is actually have a second hash set, which doesn't keep track of the visited nodes, not like all the visited nodes. It keeps track of our current path in our DFS. So I'd have a second hash set for path, and I'd pass that in to our DFS function. And what I would do is right here where we add to the visit hash set, I would do the same thing. I would add to the path hash set. Here where we check if the source has been visited, before that, I would check if the source has already been added to our path. If it's been added to the path, that's bad. That means that there's a cycle in the graph. And at that point, I would return, and I would return maybe false here instead of returning true. False means that there is a cycle that was detected. And then, when that DFS is called, whether it's here or up here, I would handle that in some case. I would say that we were building the topological sort, but we detected a cycle, so we have to return some default value, maybe -1, maybe an empty array would be more appropriate. Also, after we're done visiting that node, after we add that node maybe to the top sort, and before we return, I would pop the node from our path to basically say it's no longer a part of the path. Let me kind of show you what I mean in this drawing. We're going to start at A normally. We're going to add it as being visited. Then let's say we go down C first. We added it as being visited. We go to E, it's been visited. We go to F, it's been visited. And then in reverse order, we would add each of these to the topological sort result. But remember, we have a second hash set for path. So as we add each of these to visit, we're also adding them to the path. So we keep going down, but then, we go down as far as we can, and then we want to basically pop back up so we can add each of these values to our top sort result list. But as we, pop back up, we're going to unmark these as being a part of our path hash set. They would still be visited. That's what green means. They've been visited before, but they're no longer a part of this particular path. So we'd pop them from the path. Now, A is going to still be part of the path. And then we would go down the other branch that we haven't visited yet. We'd go down B. We'd mark B as a part of the path so far. We'd go down D, we'd mark D as being part of the path, and then we would, follow its neighbor edge over here. We'd get back to A. The problem here is that we would see that A's already been visited, but we don't want to return true because before that we'd have our if statement that checks that A is actually not only visited, it's also a part of the path. So here we would realize that we have a cycle in the graph. Down the same path, we reached the same node. We would also, maybe instead of going on this edge first, we would have gone to this edge over here. But when we get to F, we would see that yes, it's been visited, but it's not a part of the path itself because we don't want to, say that this is a cycle because yes, it's going to have been visited down this path, but it would have also been visited down this path. That doesn't mean that this is part of a cycle. That's why we have a second hash set to distinguish between the nodes that have been visited and the ones that have been visited along the same path. Because if they're on the same path, then that means it's a cycle. Okay, now before we wrap up, I just want to mention one more thing to you that will make the practice problems a little bit easier. One application of topological sort is actually with course prerequisites. For example, in college or high school, there are sometimes courses, for example, a course would be Physics 3, P3 for Physics 3. This course has some prerequisites. You have to take maybe a Physics 2 before you can take Physics 3. Before you take Physics 2, you have to take Physics 1, and maybe before Physics 3, you also have to take Calc 2. Before Calc 2, you have to take Calc 1. Before these two, maybe you have to take Algebra 1 or something like that. I'm just making this up. And maybe over here, independently of all these like STEM courses, you have English 2. Before you take English 2, you have to take English 1, something like that. This course prerequisite or course schedule problem is a really common and famous application of topological sort. For example, given a graph like this, you want to construct a topological ordering. In this case, the topological ordering of this would put these courses in an order such that you can take each course, right? Because for some courses, you have to take the prerequisites before you're allowed to take a course, right? For example, P3 in this ordering could not come first because it has some prerequisites that we'd have to complete. But also notice something about this graph. It's sort of in reverse order, right? Because what we know about topological sort, we know from an edge, we have to take the source edge first, and then we can take the destination edge. So we would build the output something like this, where Physics 3 goes before Physics 2, but that's not correct. Here we're saying that Physics 2 is a prerequisite of Physics 3. Physics 2 should go first. So this is a problem where the graph is actually set up in reverse order. So in this case, when we run our topological sort algorithm on this, we actually would not have to reverse it. Because remember what I talked about earlier, when you're given a graph, one way to get the topological ordering is to take each edge and reverse it. But in this case, our graph has already been built in that way. What I'm saying is, what we thought is that you have to take Physics 3 before you have to take Physics 2, but this edge actually represents the opposite. This edge is saying that we have to take Physics 2 before we take Physics 3, and this edge is saying we have to take Physics 1 before we take Physics 2. So what I'm saying is it's important to recognize like how is the graph built. So if I was given this graph, I would run our post-order DFS and then build the output. in that case, we wouldn't even have to reverse the output because this would build it because our post order would build this correctly. We'd get to P3, then we'd get to this layer, then we'd get to this layer, and then we'd add algebra 1 first, and then maybe we'd add these. You get the idea. So this is one application. I think this is what you'll do in one of the course schedule problems. It's one of the suggested problems that I've linked below. So I just wanted to let you know about this in case it's confusing. Sometimes you'll be given a topological sort problem where you don't actually have to get the topological ordering. What you actually have to do is maybe detect a cycle or something like that. So there can be many open-ended problems when it comes to, topological sort. You might not necessarily be implementing the topological sort algorithm.